amazing experimental math related to Smale's famous problem.
Thank you very much, Doran. Yeah, it's a great pleasure to give this talk. And in fact, it all started, let me first pull that up here. There we go. So with Doran Seilberger's 60th birthday. So actually it's not that long a time ago. See, there's here, you see, in celebration of Doran Seilberger's 60 plus square root epsilon's birthday. So square root epsilon is, of course, then it's up to you. I think it's 63 by now. So in any case, it took us a long time to write this. And I will today explain briefly what Smale's seventh problem is, what magic numbers are in here, right? So, and then, of course, also emphasize a little bit the importance of computer experiments, because most of the stuff here is based on so-called computer experiments, even though Doran may frown upon them, right? Because there's pretty much nothing really symbolic in it, right? I mean, you will see a few symbolic things.
Numbers are also symbols. Numbers are also symbols.
Yeah, sure. But the point is, it's number crunching usually what people do, right? And so there will be a few symbolic things. And but the reason I'm standing here today is really that there was some weird things we ran into when we were doing Maple recently, and so I asked Doran, what's going on here? And he said, oh, that's fascinating, you have to give a talk about it. And so that's why I'm standing in front of you today. So that will come a little bit later. First, let me introduce you briefly to what Smale's seventh problem is. So Smale was asked at the turn of the millennium to propose a list of problems worthy for study in the 21st century. And so he came up with a list, I believe, of 21 problems, if I'm remembering that correctly. And the seventh problem...
In analogy with Hilbert's. In analogy with Hilbert's.
Yeah, well, maybe it's not 21 then, I forgot. Maybe that's what was spooking in my memory around here. So anyway, it's a longer list of problems. And the seventh problem is something that has to do with point charges, and so it sounds almost like physics, but it originates in a paper by Schub and Smale on computational complexity, right? So let me briefly state what it is here. So you take R3, okay, and you take vectors xi and xj, all right, and you define the Euclidean distance between them just in the usual way. All right, so that's the Euclidean distance. All right, so now, based on the Euclidean distance, you define a certain energy between particles. If it would be Coulomb, right, in the traditional sense, then 1 over the distance would be the Coulomb energy between two charges, unit charges. All charges have the same charge here, 1, and 1 over the distance is the Coulomb law. But in fact, what, so I should write the xi's in R3. What Smale was actually doing, he took the log of this. He took the log of the 1 over the distance, and moreover, the restriction is in fact that even though the xi are in R3, but they are having all unit length. Okay, so that means they are actually on S2. So points on S2, but represented as vectors in R3. And so in a sense, well, of course, vectors in S2, but so that's what I mean. There are points on S2 represented by vectors in R3. And so then the question is this, given n points of that type, all right, and no 2 points should actually coincide, right? So there are given n points in R3, usually distinct. Okay, we define now, we call that, how about that? Endpoints we call omega sub n. Alright, so that's a configuration of mutually distinct points in R3 having all unit length. And so we define an energy E of omega n, right, to be simply the sum over all possible pairs in that configuration. So 1 less than or equal to I, strictly less than j, less than or equal to n, of ln of 1 over xi minus xj. So this is the energy of such a configuration, all right. And now what we would like to do is we would like to find the min over all possible omega n of this, which is the min over omega n. And so there is always a min, right? So this thing is by compactness and lower semi-continuity, you always have a min. And so we will call that E of n. How about that? All right, so later we will modify that a little bit. And so that's first of all what you are interested in. And it turns out, believe it or not, that this is an extremely hard problem to find the minimizers when n gets large. All right? So I have, just as a little bit of fun, let me show you a few illustrations that you find on the web. Whoops, of course, now that damn thing is gone. Let's call it back up. There we go. Thomson problem. Where's the application? Oh, that's not so nice. I had spoken with our system administrators. I should normally now open up an applet here, and apparently it doesn't. Okay, fine, no applet, sorry about that. In that case, I have to just illustrate it with my enormous graphical skills on Blackboard now. So there's a nice applet that if it would be having all the updates here, we could play with a little bit. It's called Thomson problem at Syracuse University, the physics department. And so let's just start simply. So here's S2, okay? Okay, here's the north pole and south pole. So that's not the number of particles. So start with two particles. What will be the minimizing configuration? Well, everybody knows two antipodal points, like north-south pole. Trivial. Okay. Three particles. What will be the minimizing configuration? Right? Equilateral triangle in some equatorial plane. Trivial. What will be the minimizing configuration for four particles?
Tetrahedron. Tetrahedron.
Tetrahedron. Correct. Right? So 5 particles. Now it gets interesting.
Very interesting. That is interesting.
5 is already non-trivial.
Sometimes same as 6, of course. It's sometimes the same as the answer to 6.
That's
depending
right.
on the problem.
That's right. Of course, you know a lot of this. But anyway, that's true. So sometimes like 6, right? And well, in this case, yes, it is sort of like the answer of 6 by structure. You have with 5, you have one particle here, one particle there, and then you have an equilateral triangle there. So you just stack them up.
Oh, the tetrahedron.
It's like 2 tetrahedron together, yeah. And okay, fine. 6. Well, that's easy again.
Pyramids, 2 pyramids?
That's right.
Yeah.
In fact, 2 pyramids, yes, that's an octahedron, actually one of the platonic bodies. So like the tetrahedron, the octahedron also is a platonic body. Right, okay.
7?
7?
Dibs on 8. Dibs on 8.
Could it be 2 pyramids?
Also, but now with 5, base 5, exactly. So again, like he was saying, like 6. No? So except that you get one more, right? Indeed. So it's n equals. Let's already note that down. Let me write log interactions here. N equals 5.
So for each n, it's an advanced calculus problem.
In some
principle,
sense,
within.
in principle, yes, but it gets quickly out of
Yeah.
bound. That's the point. So here I'm starting simple, right? And but I will mark this because this will come up later. N equals 5 was the let's call it the triangular bipyramid, and of course it's a regular triangular bipyramid. And n equals 7, right? Is the regular pentagonal bipyramid, right? And of course, n equals 6, I put it in quotes, regular square, that's what they call it, square bipyramid.
May I ask, just
Yes.
to keep you honest, which ones do you have a proof of? Will you tell us?
Me, I haven't.
No, but I mean,
proved
which
any-
of these do you know to be optimal?
This one is optimal to be known.
Yes, I agree.
And then for n up to n equals 4, they are all known to be optimal, and then n equals 6 is optimal, and n equals 12.
Are they all unique?
Hmm?
Are they all unique?
Up to rotations, yes. Up to rotations.
But the others are just conjectures.
Hmm?
The other remarks are
Yeah,
just
that's,
conjectures.
that's why experimental math. That's why- so this
Even
is
for 5, is a conjecture?
actually at log interactions with this constraint, I was already jumping ahead of myself. This is also shown already, n equals 5 for log interaction. But I will get later 2 more general interactions, and then it's a conjecture. And also not actually always, it's a conjecture for a certain parameter range that I will get to later. I want to stick with log interactions for now because that's Smale's problem. Okay, good. So anyway, so we note that down, and so if you keep going, for instance, next 8, what would you guess?
You
A cube, right? That's what people would guess, but it's
rotate
wrong.
Oh, no.
Twisted
It's
cube.
wrong. It's not a cube.
Twisted cube.
It's a twisted cube. You take a cube, right, and then you take one face, parallel to the, say, the upper face parallel to lower, and you twist it by 45 degrees, right, and adjust the height a little bit. Has lower energy. So not all the Platonic configurations are optimizers, right? So that's the first message. So
And that configuration that you just described is known to be optimal?
this is experimental for sure. Whether it's known for log to be optimal rigorously, I don't know, I must say.
For
Possibly.
packings, we know more, of course. If you ask for the optimal packing of 8 points, the twisted cube is optimal.
So anyway, so in terms of computer experiments, definitely twisted cube. And there's no reason to doubt it because with n equals 8, that is still easy to manage. The point is, of course, that actually people are interested in large n, okay, and then big question mark. And the reason there's a big question mark is not just because it takes a lot of time, but there's no known algorithm that surefire goes into the global optimizer. What people do is they start with a random configuration on the sphere, and then you run either some gradient flow, possibly, right, and well, until you stop. Okay, now there is only one problem, that again, empirically, the number of local minimizers of this expression here, number of local minimizing configurations, is growing roughly like e to some constant n. And that's a problem, right? So that means you get stuck much more likely in a local minimizer which is not global. So what people then do is they run their random algorithm for the starting configuration many, many times. Each time let the flow go, right, until it stops, bookmark the result, and the configuration start all over again. And then at some point when money runs out in time, so you have a long list of data, right, and then you look which one had the lowest energy, and that is the conjectured configuration. And then somebody else tries and sometimes finds a better configuration and so on. So that's maybe not exactly the optimal method to try to get close, but in the course of time people found a certain behavior empirically of this function here, this function. And so let me erase a little bit.
That's not like putting charges on a sphere, is it?
In a sense it is, but if you pretend the world were two-dimensional, because then the Coulomb law is actually ln of the 1 over distance, not 1 over distance. And so in this sense, a two-dimensional charge round universe. So, okay, now let's take that away. The point is that the energy as a function of n, right, has an asymptotic behavior. I write it as if it were an asymptotic expansion. So it starts with a coefficient a n squared. Then comes a term b times n ln n. Then comes a term plus cn plus d ln n. So that doesn't mean derivative, it's just a coefficient. D ln n plus maybe an e plus and so on. So empirically, so that looks like some kind of asymptotic expansion. What has been proven rigorously is this. For this one, there is a sharp conjecture in the sense that there's an explicit formula. And I write almost proved, so there's very little doubt that one can prove this now by, and this is a result by Smale and Serfati, Silvia Serfati. And the sharp conjecture is by Seth, Brauchart, I think Harding maybe one of the co-authors. Maybe I write et al, so it's maybe some combination of that group of people working with et Seth. So they have worked out a very careful way of estimating what this is and a very plausible argument what the exact number here is. And Smale and Serfati, they were able to control such a term in a slightly related problem where instead of the sphere, you put charges in the plane, also with log, right? So a thing of point vortices moving in the plane, and but with an external confining potential so that they don't escape to infinity. On a sphere, you don't need an external potential, of course, nothing escapes, right? But you could do a stereographic projection of the problem on the sphere because there's a conformal invariance involved, so you still have log interaction now in the plane, and from the Jacobian, from the stereographic projection, you get something that is equivalent to an external confining potential. And when you look at the asymptotic behavior of that confining potential, it just escapes the range of control that Smale and Serfati has. It's just a borderline. So they can get arbitrarily close to that, but not to the this particular confining potential. If they can twitch their proof a little bit, then they can also nail this one down.
So you have estimates for C, for the value of C?
Oh yeah, that's what I mean by sharp conjecture. There's an
Yeah.
explicit formula numerical, and that looks pretty nice anyhow already.
Right.
That's plausible. And so,
Do you know it precisely? So many digits? The estimates?
oh yeah, this is not just a numerical formula. This is really an expression that you can evaluate to arbitrarily many digits.
But it's not in terms of pi or e or...
No. It's something more complicated.
Yeah.
But it's not in any way any of the familiar numbers that students learn. So there's some zeta functions involved.
But this is an explicit expression.
There's an explicit
Yeah.
expression for this one. That's what I mean by sharp conjecture.
Yeah.
Means maybe I should say instead of sharp, how about explicit?
Yeah.
Explicit conjecture. For this one, there is only numerical evidence. Actually, for the whole thing, including that coefficient, numerical evidence, and similarly for something like this. So it's not clear whether this is actually truly an asymptotic term in the sense of asymptotic expansions, or whether this is numerically plausible right now, right? And but even if that is asymptotic, maybe this is no longer. So There are lots of open analytical questions.
But when it's obvious that it's of this form, how come it's obviously not an squared plus b times n to the power 1.5?
And you mean this?
Yeah, why the next term? Is it obvious that after n squared you have n log n?
I can explain these with plausibility arguments.
Oh, yeah.
So then it gets already.
So it's obvious that it's not n squared plus a
That's
to the power n, some b to the power n.
Are those proofs rigorous, or are they physicists' proofs? That
These
it has that form?
these two are absolutely rigorous, but
Are you sure?
Of course,
Yeah. Are you sure? Because I've seen some of these arguments, and they're not always convincing. So, who did the first getting the explicit form of the first two terms being
The
just
first?
so? Yes.
I don't know who did it first, but I can do that even today here, but then I will not get through my talk now. So this is the part of the argument I can actually write down, and that will already indicate there should be this and this term, right? For this one here, this is indeed, for physicists is very plausible, right? But these guys actually need this to get actually down to here. No? So you have to first control this, then you have to control that part, right? And to be able to actually address the third term.
But it's obviously not n log n squared term.
No, that's right. That's right. It's n square, n log n, n, ln n. That's already not so clear. No? So that's
But plausible from plausibility argument, that's why we explain.
even for plausibility argument, this comes relatively quickly. This is already a little bit more argument. And I mean, as I said, this is more numerical evidence, that you try to control this. So anyway, so now back to the title, Smale's seventh problem, right, is involved here. So what did Smale say? He said, well, if we don't have an algorithm that can find the global minimizer, maybe we have to settle for less, right? Namely with an algorithm that if you give the number of points n, then in polynomial time it will find at least a local minimizer whose energy is good enough. And good enough, he means it should not deviate from the true result by more than this term, possibly with some other constant, right? But constant, of course, independent on n. So that is the problem of Smale, the seventh problem. Find an algorithm that upon input n in polynomial time will return a configuration with energy that is not deviating from the optimum by more than some constant times ln n. Okay, so that's the problem. Good. All right. So let's see, why would he be interested in it? As I said, this is something that comes up in computational complexity, but actually problems of that type come up in a number of situations. And let me just show you a few nice things. Olympics, how about that? So nature likes such configurations apparently also. These are electron microscope pictures of pollen, plant pollen, right? So there's lots of some beautiful patterns on spheres, right? That one may want to describe, find out what kind of optimal configurations they are, if they are really optimal or nearly optimal. And but also we have oops, that comes later.
You can see they're not
Maybe.
optimal. You can see they're not optimal because of those hexagons.
Okay. Yeah, here's another virus picture. Look, that's not pollen, that's a virus. Okay. And then we have something like that from the human applications. Right, so here's a radar station, and when you take a closer look, you see that there are some, not exactly hexagonal patterns. Here's some distortion that has 7. And so designs of that type, they occur in a number of contexts, and people are interested.
Isn't the Bush bubble similar? The Bush bubble near the stadium looks like this.
Maybe. So anyway, I put that up from the web. So let's now get to the following. I said let's get to the n squared term. And then you will see that in this context, let me read that here. Yeah, okay, thanks. Let me modify that a little bit and define V of n to be simply 1 over n and n minus 1 E of n. Okay, so I'm dividing out the number of pairs except for a factor of 1/2 here, right? And so there's a simple proof result that the map n, of course you need at least n equals 2, right? If 1 doesn't work. The map n into V of n is monotonic increasing. Okay, so this was actually shown by, at least by Lankov. That's what I learned from at SAF. And the book is Modern Potential Theory. Okay, and but it's also very easy to show. Well, okay, I just take that out. So what one does is look at this expression, and we just write it as a triple sum. You sum first over all vertices, right? And write this E of omega n, let's say as a sum over k equals 1 to n over all vertices. And then in here, and we have to put some correction factor in there, in here we have to sum now again over all, let's say I less than j, or 1/2 unequal to j, but also I unequal to k. Of course, you take that out, and j unequal to k. So it means I'm taking 1 point out. I have an n minus 1 point configuration. Okay, and look at the energy of that one in this sense. And then I sum over all of them. And when you take a simple picture, let's say I do it with 4 here only. Okay, let's do a complete graph. So that would be assign some numbers to all these edges, and that is your energy here for the configuration. Now, what do? I first take out this one, and I get that graph. Then I take out the upper part here, and so on. Schwupp, schwupp, schwupp. And one more, plus, now the last one is the lower one is out. So, and you put them all on top of each other, and you see that at the end of the day, all the edges are there again, but there are now too many. Each edge occurs actually too many times, and when you think about what happens each time I take a point out, of course, then 1, 2, 3 edges disappear, right? And so that keeps going, but each edge, however, is taken out twice only. Namely, if I take out this point, for instance, this edge here, now when is it gone? If I take out that point, and if I take out that point. So there should be a 2 involved, even though this is, of course, a picture with only 4 points. So in total, I'm overcounting here, in fact, by n over 2, and I have to correct it for that. And then here, of course, blah, blah, blah. This is the E of omega n, and I should say without the kth particle, right? So I take the kth particle out here with some funny notation. Or maybe xk, without xk. So, okay, now I minimize here over omega, right? So it's still the same as the min here. But now I do one thing, I pull the min in. Okay, and you know, of course, that the min of a sum, right, is always bigger or equal at best than the sum of the mins, right? And that's the only inequality actually, in some sense, you are using. Now I have 1 over n minus 2 here, and sum over the k is from 1 to n. And then down here I have the min, and now I carry out my min, right? But this is now the min of an n minus 1 point configuration. So in total, of course, I can write actually this, because it doesn't matter which one I've taken out, it's always an n minus 1, and if I minimize, I always get the same number. So this is always the same, doesn't depend on k, so I can take this out and put an n here. Now I divide this by n and n minus 1. Well, do the same thing. So it's a little bit tight. So, and here divided by n and n minus 1. And you see I can now cancel the n already. And of course, well, here it's the other way around. I should write 1 here and 2 there. Schwupp. And we are done. This here is, of course, Bn, B of n. And this here, whoops, this here is V of n minus 1. And for this game, I had to assume that n is at least 3, of course, because V of n minus 1, of course, has to be n minus 1 at least 2. So that's it. Very simple proof. All right. So now, next, one can write V of n also as a minimum problem in a double integral. Actually a single integral, and I have my ln of 1 over x minus y, and I take a 2-point measure of dx dy, and I go over s squared. Well, actually, I think if I write like this, there should be 1/2 here. And so what I can do is, if I plug in indeed the empirical 2-point measure for n points, right, then I get back exactly this expression. On the other hand, I can estimate this, that this is surely below now 1/2 double integral, again this S2 here, ln of 1 over x minus y, and instead of any 2-point measure, now I take a product of 2 1-point measures on the sphere, dy. In particular, I can make it very simple. I can just assume a uniform measure on there, right? And then this is integrable locally, and surely S2 being compact, also you have no problem for long distance divergence. So this is less than some number. Okay, so now you have a monotonic increasing sequence of numbers bounded above, it has to converge. And since, of course, you divided e over n by leading order n squared, that's exactly the n squared term that you get. And in fact, with a little bit more effort, you can show that in fact this number here, when mu is a uniform measure, is exactly the a in the expansion that I wrote down. So that part is actually relatively easy. For the other parts, then, well, on the other hand, one sees already there will be an order n contribution from here also. The n ln n is a little bit more tricky because of the strict time limits. Let me skip that part and keep going on. So, now, what was then our motivation to get started into this? Well, one thing was that this monotonicity proof that is very useful for a number of other purposes, but once I was working with this monotonicity, I realized I could use it as a test criterion to check these empirical numbers that people find running computer experiments, right? And indeed, I was looking through lots of these tables published, and I found 24 non-monotonic numbers. That means where these random algorithms, right, after running it several thousand times, and people come to a conclusion this is putatively an optimum, right? When you compare it with the previous n, right, so then you see that suddenly, bloop, you fall down, you violate monotonicity, so you know that previous number had to be wrong. and you get also an upper bound by just pulling back, right? You know what it at least has to be better off. No? So that was a good application. And so then this got then triggered by the following idea to find the next best criterion, namely now you have a monotonic increasing sequence bounded above, so overall, if you plot it, it must be overall concave. And here are some pictures of these empirical sequences. Here's in particular log n. So I have to switch off the light. All right. So this is this V0 here stands for the log. X upstairs means experimental. So these are experimental data, and the formula is indeed the minimum of this divided by n and n minus 1. And so this is the numbers you find by looking at up to n equals 200. These are data taken from a paper by Rachmaninoff, Zaf, and Tsu, and from a PhD thesis of Mr. Tsu. And you see, indeed, Jesus, this looks nicely concave. Over. Question, is this perhaps strictly locally concave? Right? So that's something for the human eye that's plausible. Don't mind these little jumps here. This has to do just with the way of plotting it. So this is not real, this little jumps there. But indeed, if you define the second derivative, not define, we evaluate the second discrete derivative, then you find this. And you see that, all right, here it's the second discrete derivative is negative, but there it pretty much hits 0, and this one is clearly above 0. And then it's hard to say. It's really very near 0. And so, indeed, it turns out that this is not exactly always locally concave, but there are defects, every now and then convexity defects. And if I call up our paper again and I pull it down, there is actually a nice sequence of numbers. There's more of that. Let me see. Oh, this is. Come on. Da. Look only at the upper line. The 0 here refers to log, and C means convex, C plus is convex, and X for experimental. So here's the number of n at which you have a convexity in the energy per bond, right, of the putatively optimal configurations. So 6, 12, 24, well, 32, sorry, 48, good, 60, 67, 72, and so on and so on. Well, 67, an odd number. So far, mostly the stuff was all even. But there's another funny one. There's 137.
Is that in the OIS? Is that in the OIS?
No. That's in the OIS.
It is?
Yes. And so...
Is it even well defined? Well, of course it's well defined.
It's well defined, but
you don't know many terms.
That's right. That's what I told you. That's why I asked you, can we actually even upload it? And then you told me, well, somebody already did upload it. So that happened. I wasn't even sure we should upload it because these are experimental numbers. So the first ones you can pretty much trust. There is absolutely no reason to doubt that the computer experiments find the optimum.
But officially it's still conjecture.
Officially this is a conjecture, but they are in principle absolutely well defined, and in principle one could figure out what exactly the so-called convexity defects numbers
right,
are.
the logical possibility that the 6 is 5. It's still a logical possibility that the 6 equals 5.
Yeah, but the chances I think are very slim. It's much more questionable whether something out here is actually correct. And but the interesting thing is when you think back, take the table of the chemical elements, right? So periodic table. So there are these very nice periods in there, and then the nuclear physicists, they have magic numbers. That means particularly stable configurations in nuclear physics. And so here we have something like a two-dimensional Coulomb law. So we call them the magic numbers in Smale's seventh problem, because what does a convexity actually mean is that to get to the next configuration, to put another particle in, right, you have to increase the energy per bond over proportionally to what you had actually previously had to do to get to that configuration in the first place, right? So that indicates that one may actually build up with n more and more symmetric configuration in a sense that are at some point optimal. And then when you want to put one more, you have to destroy an overproportional amount of symmetry and pay a price for that, and then it jumps up. And then you enter a new regime where it tapers off, builds up a better and better configuration until it's there, and then if you want to put one more particle in again, you pay a lot price and you jump up again. So there's a certain plausible similarity between the magic numbers in nuclear physics, and that's why we call it. Now it gets more interesting. You see there are other things. There is 1 here, 2, and so on, and 3. And if I would scroll it down, actually you see there are more and more of these numbers, and they are less and less nice because there's more. But one interesting thing is that what we did is, so we looked, instead of the log, now we looked at the so-called Riesz energies. What is a Riesz energy? Well, we call them standardized Riesz energies. And let me take the min out here. And instead of a log, what we do is we put a power s here, subtract a 1, and put a 1 over s in front. Okay? And we put an s down here. So now, this would be the Riesz energy of a configuration, standardized Riesz energy of a configuration. And of course, we also divide again by n and n minus 1. Right? And then write Vs of omega n here. And in fact, then when you take the min of all this, right, so then it becomes just Vs of n. And so you can play the game again and ask what happens next. And so there's something empirical that happens, namely if you choose s to be -1, right? So by the way, s equals 0 is not a log. That's why you see that 0 up here, right? So s equals 0 is a log here by taking a limit. But you can also put s equals -1. So then this, of course, pops up into the numerator. So it's a distance, but there's a 1 over s, so that makes it negative. So it's still a minimizer problem, right? So so you're asking basically for the configuration of optimal average distance between points. You can optimal in the sense of largest average distance. So let's see what happens in that case. And here's, all right, here's the empirical data, right, for this object here now when s is -1. And you see again overall more or less concave. What about the second derivative empirically? So we looked at the second derivative, and whoop, it looks, this time there is no peak. Well, there's a little bit of peak, but it's actually not above 0. When you look really at the numbers, this is strictly negative. So, could we prove this? Nope. Unfortunately, we were unable to prove it. We were able to prove upper bounds on the second discrete derivative, but these upper bounds are not good enough. They go to 0, but they are actually positive. And so that's not good enough to prove that that thing is actually negative. But we were able to show that if you go one more step, and that's actually super easy, instead of s equals -1, you take s equals -2, then it is absolutely strictly locally concave. You can prove this, and that's very easy because then the energy is quadratic, the derivative is linear, you get harmonic forces, and linear is easy, right? So that's explicitly computable. For s equals -1, we were not able to show that this is strictly concave, it's purely empirical, okay? So, but this explains why we have this many more numbers here, right? So there's then, when you now go to the other direction, now s is 1 instead of 0, whoa, there are many more convex defects. If you put s equals 2, even more. S equals 3 down there, even more numbers. So, and it turns out that each large set contains the previous one completely. But you see, actually, there are some numbers here that are in fact bold-faced numbers, 197 here, 177 and so on, because Then it's here this guy and this guy and this guy, because this was not actually the original set of numbers. These were missing. Okay, these were missing, so we have this set theoretical monotonicity here empirically, but these numbers were missing in these sets. And then we thought, maybe it means that these empirical data were not good enough. And so we did our own simulations using the Syracuse University website, the Thomson applet there, and we indeed found better configurations with better energies. When we plugged them in, these numbers appeared. Right? So that means, again, another new monotonicity result. Empirically, nothing is proven here about this, but taking it seriously, we were able to find 3 outliers that were not optimal. What we found has better energies. We don't know, of course, whether that now is optimal. Right? Okay. Good. So monotonicity in this context is pretty nice. So I have, now it's 48 roughly, or 47?
Yeah, 48, we have 2 more minutes to start.
2 more minutes, good, very good. So now, one last thing. I had written this list, n equals 5, n equals 7, and so. And the interesting thing is, if you change s now, then something very interesting happens when n is 5 and when n is 7. If, in the other cases, 2, 3, 4, nothing happens. So these are universally optimal configurations. 6 also. 5 is not. 5, we had this 2 tetrahedron, right? If I make s bigger and bigger and bigger, eventually, when I think it was 15 point something, something happens and it becomes a pyramid with a square base. That is, has a better energy than the 2 tetrahedron on top of each other. Okay? But empirically, that's what it is. But the whole picture has not been proven. It's, only in some special cases one knows the optimizer.
And that's good, it's empirical. Then it fits the seminar. You work and prove it, you would like it.
That's right. But n equals 7 is much, much more interesting. It's amazing what is going on. So we have this pentagonal bipyramid for the logarithmic kernel, and that seems to be the optimizer for s between 0, that's the log, and s equals 2. When you go a little bit beyond s equals 2, there is a bifurcation. Unfortunately, cannot show it because the applet is not running, where suddenly it becomes a distorted pentagonal bipyramid, and you go until s equals, what is that? I forgot. Anyway, a little bit larger than s equals 2 then, where you go into a new configuration, also a bifurcation, a reverse bifurcation, which is optimal. And then there's a crossover, not a bifurcation, at roughly 5 point something, where you jump to another optimizer. On the other side, if I make s less than 0, negative, there is also again this bifurcation of a distortion of the pentagonal bipyramid, but if I go all the way down to -2, it becomes the pentagonal bipyramid again. Right? All empirical, and we did a bifurcation analysis to find the stability points, the bifurcation points, and that's finally where something weird happens. We have 2 different Maple programs that do find numerically the same results to 20 digits precision, but only if we ask for 500 digits precision. So this one thing converges quickly. The other thing, when with the same number of precision we asked 50, we got different results. We thought we did something wrong. Couldn't find what we did wrong, and then we simply started asking for more digits of precision, and eventually when we had 500, then it was clearly the same answer. When we went to 1000, we got even better agreement, of course, but ridiculously few digits agree compared to the number of digits you asked Maple to compute, right? Normally you would think, okay, ask for 50 digits precision, we had 48 good numbers, and the last 2 are round-off errors. No, not here. You have hundreds of digits of round-off errors.
It's a very complex computation.
Yeah, it's you compute determinants of large matrices, right, and then have to find, with a parameter, find the lowest 0, right, and then have to check where does that thing become negative, the lowest 0, right? Okay, that's it.
Thank you very much.
12 points is
Thank you for a
not.
perfect experimental talk. And Michael, be glad to answer questions in 5 minutes.
12 points is not.